All right, good morning. Welcome back to Pre-Calculus. I'm just doing a kind of eclectic collection of different problems that we have here. This is about geometric series. So a lot of you guys have asked about like, well, what's the curveball going to look like? I know that the book does not give us a lot of geometric series that have irrational numbers in them. So that's the curveball. So this works for test 3 as well. Okay, so this would be a good one to pick. Okay, 1 over pi would also be good. 1 over e would be a good one to pick. Okay, 1 over square root of 5, something like that would be a good one to pick. Anything with irrational numbers in it, because students tend to have a bit more problem with that. You shouldn't, but people do. Okay, so geometric series. One of the ways we figure out, like, how do we figure out the formula for a geometric series? And I'm sorry, this is one of those that you will have to memorize because it is something that's going to pop up on a regular basis for you in Calc 2. So the way we figure out the value of a series is we just say, well, we assume that there's some kind of a thing this adds up to, okay? And what we're going to do is we're going to cap this. We're going to say n is going to be a finite number, okay? N is, we'll say element, we'll say finite. Because you have to, when you're dealing with infinite series, you'll have more of this when you get to Calc 2 than now. But the problem with infinite series is, like, if it doesn't converge, then everything I'm going to do is complete nonsense. Okay. So if I cap it and I say we're only going to add up the first 500, that's going to convert. That's going to be a value. We're going to add up the first 5,000. It's going to be a value. If I say, well, let's not let it be finite, let's allow it to be infinite. Well, then I don't know if my series converges or what they call diverges. And diverges just means that we don't have an answer for it, okay? It doesn't necessarily go off to infinity. That's a big thing in Calc 2 when you get to it. It's like it diverges. Like, well, the series 1, 1 minus 1 plus 1 minus 1 plus 1 minus 1 dot dot dot. Okay, clearly it's either 1 or 0 depending on which collection of terms that you take. But since it never settles on an actual value, it just ping pongs back between 0 and 1 depending on which ones you've taken. It never settles on a value, and we just say it diverges. Okay, it doesn't coalesce to one specific value. Now, it's not shooting off to infinity. It's not shooting down to negative infinity. It's just ping-ponging between 0 and 1 forever. We still see it diverges because it doesn't converge. It doesn't coalesce to one single value. So if I set my n to be finite, okay, we have AR plus AR squared plus AR cubed plus dot dot dot. AR to the n. Okay, and remember, n is a finite number. And what I'm going to do is I'm going to multiply r times s. So that's going to say, oh, well, let me go ahead and add this one. So I'm going to go ahead, I'm just going to add one value to this. It's still finite. Okay, if I multiply everything here by r, this a times r is now going to be ar. This a times r is going to be ar times r, which is ar squared. This AR squared is AR squared times R, which is going to be AR cubed, dot, dot, dot. And then we're going to have an AR to the n. Well, we're also going to have plus an AR to the n plus 1. Okay. So what we're going to do now is we're going to say, well, what I would like to do is I would like to say, well, what if we take S minus RS. Okay, now here's the key. This is how we're going to prove what the formula is. But this only works if, first off, n is a finite number for now. Okay, later on we'll be able to say it's infinite, but for now it's finite. If your sums are not convergent, then you cannot add them like this. Okay, we can add two numbers. Okay, but if they aren't numbers because they're divergent, okay, I don't know what value it's going to be, we can't add them. Okay, I'm always reminded of one of those commercials where it's like, what's purple plus Tuesday? Like, I don't have an answer for you. Okay, I can't do that. So if I don't have numbers I can put in here, then this is meaningless. This is how you get nonsense, like when they add up 1 plus 2 plus 3 plus dot dot dot, all the positive integers, and they get to negative 112. I don't know if you guys have seen that proof with heavily quotation marks there. Um, but the way they get away with this nonsense is that they assume that there's series that converge. They assume that they're values when they don't actually converge. They use this one actually in here to help show that this is true. So you can see what kind of nonsense you end up with when you end up trying to add things that don't converge or do manipulations on things that don't converge. So be very, very careful about, well, does it converge? So there is no corresponding term for the A. So we're just going to have A. But the AR and this AR, they're going to subtract from each other, okay? S minus RS, S minus RS. That's going to be 0, okay? All the way up to AN, that's also going to be 0. Now we're going to have minus A to the RN plus 1, okay? That's 0 minus this piece here, okay? That's S minus RS. Okay, and at that point, what we could do is we could say, well, S is common to both terms here, so we're going to say, here's S, 1 minus R, okay, and that is equal to A, okay, and then we're going to go ahead and factor out this all together, okay, so that's going to be 1 minus R to the n plus 1 divided by 1 minus R, okay. Now, if this is a calculus term, okay, what we do is, I'll say it the poetic way. We'll say, as n tends towards infinity, okay, in calculus terms, they're going to say, as we take the limit, you will grow to hate that word, as n approaches infinity, or as n goes off to infinity, what's going to happen? Well, if your R, absolute value of R, is less than 1, it's what layfolk would call a fraction. Okay, if you're a math person, this is one of those things that always bugs me, and I have to remember, like, don't say anything. It's like, it's a fraction. Like, well, 5/4 is a fraction. That's not what you meant. Okay, so we have to be careful about that. But what mostly people would say is a fraction. So they mean a third, a fourth, a fifth, that kind of a thing. All right. If I take a number that's less than 1 and raise it to a power, we're going to get a small number. Okay, if we take 4/5 and raise 4/5 to like the 100th power. Okay, let's see what that would look like. 4/5 is 0.8. Okay, and I raise this thing 0.8, okay, to the 100th power. We're going to get a pretty small number. Say to 100. Okay, great. Okay, beautiful. I'll probably put 2 decimal places in there. So 0.8, we'll do raised to the 10th power because I know the calculator can handle that. 11th, whatever. But it's 0.08. Okay, if I take 0.8 and raise it to 20th power, it's going to be even smaller, 0.01. If I take 0.08 and raise it to the 50th power, oops, just 50, it's going to be even smaller. Okay, times 10 to the negative 5, we're getting small. So if n is allowed to go off to as big a number as you could think, okay, and as you're learning your calculus, I recommend pick your favorite, find a favorite big number for you. Okay, if you're into politics, it could be whatever our national debt is, which is a few billions. If you're into chemistry, I always pick Avogadro's number. So my favorite big number is 6.023 times 10 to the 21st power. That's my big number. Okay, so that's what we say. As n tends toward infinity, and I would think this number. Okay, one more. Okay, and that's what I would kind of plug in there. Okay, but you can think whatever big number you'd like. And in probability, a big number would be something like 10. Okay, but for your calculus problems, pick your favorite big number. Find a favorite big number. Find one that you can plug into a calculator. Like a Googleplex is a nice big number, but a 1 raised to a Google or 100, that's not, or 10 raised to a Google, that is not going to be a fun, or Google raised to a Google. Fun number to say, not a fun number to punch in your calculator. Okay, but think of a favorite big number. But what's going to happen here is this number here, as n goes off to infinity here, this plus 1 isn't really going to matter. Okay, it's like, well, if it's to 1,000 or to 1,001, it doesn't matter. But this number here is going to go off to 0. Okay, it's going to get to be a smaller and smaller and smaller number. So my series here, okay, is going to be S is equal to A over 1 minus R. Okay, and again, R is a smaller number than what it's what a layperson would call a fraction. That's a convergent value. That's a number that we can calculate out. Okay, so we are allowed to do things like add geometric series together. It's one of those well-known results that almost everybody takes for granted. Okay, so it's one of those things where it's like, yes, we just know that geometric series happen to converge, provided that R is less than 1. Okay, if you don't know that it is, then you can't do this little trick of this, which is why we used a partial sum. And I said, well, let's take it to n is equal to 20 first, or n is a finite number first, because adding up a finite number of things will give us a finite sum. So we're very careful to say, let's make n is equal to a finite value first, do this calculation, because if it's finite, it converges. Then we can start messing around with taking limits and thinking about infinity and all of that other stuff. Okay, now we're allowed to go ahead and say, now we know it converges, now we have a little bit more liberty to do what we want with this series. Okay, so be very careful when you get the series. If it doesn't converge, you can't go off and start adding them. Again, nice non-convergent, a nice divergent series, 1 minus 1 plus 1 minus 1 plus 1 dot dot dot. Okay, it doesn't shoot off to infinity, but it never coalesces to one specific value, whereas something like the geometric series we've dealt with before, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 does coalesce to a specific value, because A is 1 and then R is going to be 1/2. So let's say, okay, it's 1 over 1 minus 1/2. Okay, so that's right. 2 halves minus 1/2, that's 1 over 1/2. Do our proper fraction here, 1 divided by 1/2 is equal to 1 times 2. We end up with 2. So that one works out just fine. Okay, so in the problem, it says, go ahead and calculate out for e over pi. Is e over pi a bigger number than 1? Or is e over pi a smaller number than 1? Well, e is 3-ish, right? And pi is a little bit more than 3-ish. So this, whatever fraction this is going to be less than 1. Okay, and we can properly put it in the calculator and go ahead and figure that out, and that's fine. Okay, second function, ln, where's my L? There we go. There's e to the 1. Okay, and then divided by second function pi, we get 0.86. So it's like it's kind of like 4/5-ish. Okay, it's in there. Okay, but it's less than 1. So this series will converge. So when I ask you, like, oh, can we calculate this out for when n equals 10? Sure. And what I'm looking for you to do, okay, is to go through and say, oh, look at this. When n equals 10, all we do is we place the n with a 10. So we're just going to say a is going to be 1. Okay, then we have 1 minus e over pi raised to the 11th power divided by 1 minus e over pi. in the infinite values, right, this and is going to go off to infinity. So this ratio here is going to go to 0 because it's less than 1. If I raise it to a bigger, bigger, bigger power, this is going to get smaller and smaller and smaller. So we have 1 over 1 minus e over pi. So we can say that's pi over pi minus e over pi. So that's pi minus e over pi. So we have 1 divided by pi minus e over pi. So we're going to say this is pi over pi minus e, and that would be our answer for this geometric series. This is what it's going to converge to. Okay, so we can treat that sum as this number right here, even though that's not really how we wrote it. Okay, so if you're asking for like, what's going to be the hard problem, almost always the problems in your book look like 1, half, fourth, etc. But they don't ask you too many irrational numbers. I will ask you an irrational number. So that's what your problem is going to look like. Okay, but it's not so bad. If you've done a little bit of practice, you'll get that. I try not to screw around too much with the notation for these things because some books count at 1, some books count at 0, and it's hard to keep track of like, well, which way does your book do it? So we have to kind of backtrack and remember like which and how it works. So that's not where I'm trying to trick you. I'm trying to trick you into, do you know that e over pi is a number less than 1? Do you know how to handle it if it doesn't look like it's numbers? Okay, even though it is. Okay, so that's how you do that problem. So again, I really do urge you to do all of these things yourself first and then try them and then see if you're getting an answer that is reasonably close to mine. And if you are, then that's great. You're doing fantastic. Okay, and if you're like, I don't know where to start, most of the problems I like are when a student looks at it. I don't want to defeat you, but it's easier not to grade something than it is to grade something. So if I could put a problem that looks intimidating where people will say, yeah, I'm not doing that, that's easier for me, even though this is entirely a fair problem. Okay, even though it looks scary. So don't let me intimidate you. Okay, don't let me do that to you. Say he's trying to trick me. I'm gonna get through this. Right? I know you can do it. So I'll see you in the next video. Good luck.